who is now in Maryland and used to be in UCLA. And Artem actually somehow appeared in Germany like someone, ein Wandergeselle in German. After you do your apprenticeship, you go and wander around, and then you become a master. And he did his PhD eventually in Lyon under Itai Ben-Yaakov, and then moved to the US. And so we're very happy that he will talk about Erdős geometry and model theory.
Thank you very much. Thank you to the organizers for inviting me. It's a great pleasure to be back in Münster, and especially in this beautiful venue. So indeed, I will talk about, I guess this is a logic talk in this conference, but I will try to convince you that logic might have something to say about things that you care about. So I want to start with a very simple historic question. So given two sets, let's say just two sets of real numbers, we can look at all possible sums that I can form. So I will denote it as, A plus B. So all the sums where A comes from A and B comes from B. Similarly, I can define the product set, A times B, okay? So how big can these sets be, assuming that A and B are of size n? Okay, so this can be at most n square, obviously, right? At most, that's clear. Okay, but turns out you can also achieve n square sometimes. So for example, if I just take all the natural numbers from 1 to n, what are the sizes of these sets? Well, if I look at the sums, you can see that if you take any two numbers between 1 and, let's say, n over 2, their sum typically will fall into this set again, right? So then effectively we get that the size of the sum set is just bounded by some constant times the size of the set itself. Okay? On the other hand, if we look at all the products, we can see that this is going to be as large as possible. Because you can, for example, look at the number of primes in the set between 1 and n. So this is roughly n over log n, right? And if you look at the products, you can see that the product of any two primes is unique, well, up to permutation. So you have to divide by 2, right? But this shows that the lower bound is going to be roughly n to the power 2 minus something going to 0, right? So we get the set of sums is as small as possible, and the set of products is as large as possible, okay? Now, if you look at, well, first of all, this generalizes to arbitrary arithmetic progressions. So this is an exercise for you. Similarly, if you look at geometric progressions of length n, you're going to get the exact opposite situation. So the set of products is going to be as small as possible, but the set of sums is going to be as large as possible, okay? Well, turns out that one can extrapolate between these two situations. And this is a celebrated sum product phenomenon established by Erdős and Szabó, which tells you that if you take any set of reals now, any set of reals of size n, then at least one of these two, the set of sums or the set of products, has to be significantly bigger than the set itself, okay? I don't get the square here, but I get at least something strictly greater than 1. So the exponents are strictly greater than 1, where C is some absolute number, independent of the set that I'm looking at. Okay, so this is expansion. Either I have many products or I have many sums. Okay? And conjecture widely open that this should also be essentially 2, or at least you can get to the power 2 minus epsilon for an arbitrary small epsilon. This is widely open. Okay, it's an old question. Okay, but I mean, very simple question, but not simple to solve. Now, is it just about addition and multiplication, or is something more general going on? Well, you can look at a bivariate polynomial, okay, and try to do the same thing. So take two sets of real numbers, let's say a and b, and let's evaluate this polynomial on all possible pairs from these sets. Okay, so how many outcomes can you get this way? Well, the idea is that intuitively, a typical polynomial contains both addition and multiplication in some form. So again, it should somehow grow, right? We should still have the expansion happening. There's an obvious counterexample to that. Namely, you can look at an additive polynomial, which is essentially just a sum of some univariate polynomials. Or you can look at a multiplicative one, which again somehow just contains a product of univariate polynomials. So these are cases in which addition and multiplication are not really mixed. I mean, they don't really involve two variables at a time somehow, okay? So in these two exceptional cases, we don't get any expansion. By the same argument as we did earlier, for example, with arithmetic progressions, you can see that the size of is going to be just some constant times n again, okay? But turns out that these are the only exceptions. So as long as there's any mixing of addition and multiplication, we're going to have expansion again. So this is a theorem of Elekes and Szabó. So it tells us exactly this. So if I have any polynomial in two variables of some degree d, which is neither additive nor multiplicative, as in the previous slide, then the size has to be strictly bigger. So I get non-linear exponent, yeah? We can get for thirds. Again, this optimality of this is not known, but it's known that you do get some non-trivial expansion when you apply it to a pair of sets of size n. Okay? And there are various improvements of the bounds that appear here. There are many variants of this that happen over C, for example. Over complex numbers, you get the same instead of over reals. And you can see somehow we have these two groups interacting, plus and times, right? The additive and the multiplicative group of a field. So this somehow gets explained in a very elegant and conceptual way by a theorem of Elekes and Szabó, so which I want to state now. So this is a result which somehow tells you there's a strong dichotomy. Okay, the setting is the following. Assume I have an algebraic surface in R3, let's say. Okay, R3 is not so important here, but in the simplest possible situation, let's say I have an algebraic surface is in R3, excuse me. Okay, and assume that projection on any two of the coordinates is finite to 1. Or let's say just generically finite to 1. But for simplicity, really finite to 1, let's say, okay? So then again, if I start intersecting it with sets, finite sets, let's say of size n by n by n, okay, so direct products of triples of sets, because of this finite to 1 condition, I cannot expect to get more than n squared, right? Two coordinates are going to determine the remaining one, okay? But then the question becomes, when do I get this maximal possible size of the intersection with a finite grid of points like this of my surface? Okay, and there are two possibilities, namely exactly one of the following two possibilities holds. So either I have what I will refer to as power saving. So we get that the intersection with arbitrary finite grid of size n by n by n is strictly smaller than the maximal possible one. More precisely, we have some particular exponent, gamma, fixed independently of the grids I'm looking at, so that the power is bounded away from the maximal possible one by this gamma, by this positive gamma. Okay, this is one possibility. So there's a gap, power saving. Or another possibility, my relation is essentially the graph of addition. Okay? When I say essentially, here I'm going to state it with in a local version. So what I mean by this is that we can choose open subsets containing 0. So we have some neighborhoods of identity in the additive group, so that we can map coordinates one by one. So we have these coordinate-wise maps, pi I. And so that my relation holds precisely when the sum of those three is 0, when the sum of the images is 0. Okay? So up to this coordinate-wise bijection, this is essentially the graph of addition. Okay? There are some alternative versions of the theorem, and there are two main regimes which I might jump between sometimes. We can look at the same question, but I can work, for example, with an algebraically closed field, and I can look, in the case of an irreducible polynomial, instead of these local correspondences, I can actually get a global correspondence. At least generically, yeah? I can get this finite to finite algebraic correspondences. So somehow up to finite noise, again, I would get that this is essentially the graph of a group. And to return to this example with arithmetic progressions, which we saw earlier, this is a particular case when my surface is just given by the set of zeros of this simple polynomial. Yeah? Okay, so this Elekes-Szabó provides somehow an explanation that some groups appear in these situations when we just try to count the sizes of the intersections of our surfaces with finite grids of points. Okay? Now, this theorem has caused a lot of activity in the last decade, okay? Because, okay, it's about dimension 3, what's going on here. So just to give you a slide of the activity in the last decade, you can see a lot of people worked on it. So the natural way to ask, natural generalization of this question one can ask is assume now I have a bunch of sets, x1 through xr. So let's say I have a bunch of varieties, all of some fixed dimension m. I mean, we can make the dimensions different if you want, but for simplicity, let them all be the same dimension. And I have my relation R, which is now not ternary like we had earlier, but it's of some arbitrary arity. Okay? So I have R, which is a subset of the direct product of a bunch of varieties of dimension n. Okay? With the same assumption that essentially the codimension is 1, which we formulate in this strong form that the projection onto any r-1 coordinates is finite to 1. Okay? When can we again capture that this is essentially graph in some algebraic group? So first of all, note that the dimensions are now arbitrary of my somehow of the parts of my relation. So one cannot expect to reduce it just to addition on the real line or on the complex numbers. Okay, and so there was a lot of activity. People kept improving arities or dimensions. I want to highlight the first appearance of model theory in the picture. Was a new proof of the Elekes-Szabó theorem given by Hrushovski, the original Elekes-Szabó theorem, which somehow brought into the picture some very central ideas in model theory, which I'll try to say something about later. But somehow, in particular, it highlighted the importance of the notion of modularity, of certain matroid or pregeometry that can be associated in the limit to this kind of variety that we are looking at. Okay. I also want to mention a result by Bayes and Brouillard, which actually they carried out while I think they both were here in Münster, so maybe, yeah, it's, which proved a rather general result of this form, but the method was completely, well, the method didn't provide any bounds. That was, so this power saving, the gap between maximal possible power and the power you get in the non-group case, they proved it exists in this rather general regime, but nothing was known about it, okay? And for many various combinatorial applications, it's quite interesting to actually know particular bound. Okay? And today I want to present a result from a joint work with Peterson and Starchenko and survey some of the ideas that go into it, which proves a general version of the theorem where both the arity and the dimension are allowed to be arbitrary. And moreover, not only we look at polynomials, but in fact we look at something more general, namely definable sets in no-minimal structures, okay? Which I will say a few words about. Okay, so first I want to state the one-dimensional case. It's very similar to what we already saw in the case when our relation just had RET3. Okay, so assume I have arbitrary R now, and I have some, and let me even say semi-algebraic set. So defined not just using polynomial equalities, but also inequalities, let's say. Okay, some semi-algebraic set with the same assumption: projection onto any r-1 coordinates is generically finite to 1. Okay, what can happen? Well, the maximal power is r-1, right? Because r-1 coordinates are going to determine the remaining one. So either I can have that the power is strictly smaller than the maximal possible one, and these are explicit bounds if you care. Okay, so there's actual explicit gap. Or what happens is that locally again we can put our relation in a coordinate-wise correspondence with addition in some neighborhood of the identity. Okay? So this is just a higher arity version. Now, what happens if my relation doesn't just live on the product of the copies of R, but if it lives on a product of some varieties of higher dimension? So here there's a new thing that needs to get introduced. So I need to look somehow not just at arbitrary grids anymore, but I have to look at grids in general position or in generic position. So what do I mean by this? Well, intuitively, this just means I want to look at grids so that if I try, so that varieties of smaller degree cannot cut out many points from them. So somehow I want to avoid all this lower dimensional mess that can be introduced by this, okay? One explicit way to formulate it is as follows. So let's say I have all my parts xi of dimension m, and let's say it's bigger than 1. Then I will say that a set A is in d new general position, where d and nu are just some natural numbers, if whenever I take some algebraic subset of x this should be x, excuse me, just x for a second. If I take any algebraic subset of x of strictly small dimension, so dimension smaller than m, then it can cut out at most new many points from my grid, okay? So all smaller dimensional varieties can only cut out a bounded number of points from my grid. And we say that a grid is in a general position, or the new general position, if each of the sets AI is in the new general position, okay? So I want to look at these grids with this added genericity to them. Now, why did it didn't matter in the one-dimensional case? Because in the one-dimensional case, if I fix my degree d, then all sets are going to be in general position as long as nu is large enough, right? I mean, this simply because a polynomial of degree d can only see d many points or the complement of d many points, right, somehow. So in one dimension, this is irrelevant. But when you go to higher dimension, this becomes a necessary thing to look at. Okay, and now this is the general result. So the situation is the same as we had earlier in the one-dimensional case. But the only distinction now, well, I highlighted in bold font. So the first distinction, now I'm assuming that my sets xi, the sides of my hypergraph are somehow of arbitrary fixed dimension m, okay? Then I get again dichotomy between being related to a group or having some power saving. But I only get power saving on grids in general position here. So namely, I can choose some number d, just depending on my r, or rather on the degree of the polynomials involved in r, such that for any choice of nu and any grid in the new general position, I have again strictly bounded away from maximal power of the size of the intersection. Okay, so this is the first possibility. I get power saving on grids in general position. Or I get that, again, my graph up is essentially up to this coordinate-wise maps is the graph of addition in some abelian Lie group. Okay? So we do keep abelianity, but now I have to look at groups of dimension m corresponding to the dimension of the sides of my relation. Okay? And you can choose these maps, the bijections between my neighborhood and the group, and the sides of my initial variety. I can choose them to be, for example, homeomorphisms, with analytic inverses, etc. So I can choose these maps to be really, really nice. So it really tells you that the relation is of this very special form somehow. Okay? So it's a funny fact. Somehow the extremal situation, the extremal combinatorial situation, a counting question, can only come from robust algebraic structure. Okay? This is a phenomenon which is known actually to exist in some questions in extremal combinatorics, but this seems to provide a quite systematic way of recognizing it. Okay? So this is the main theorem. It's okay with everyone, this statement? Okay. So then I want to make a couple of remarks about it. So first of all, it's not just about polynomials. Okay? In fact, as model theorists, we work in a more general situation. We work in a structure where we're not only given the field operations, but we're also given some arbitrary additional operations. So for example, the exponential function, or I can have some analytic function restricted to some bounded interval. And structures of this form are called minimal, and they satisfy very nice geometric properties. In some sense, they are viewed, I think, today by people from number theory, for example, or algebraic geometry. They view it as some kind of, a possible solution to this Grothendieck's tame topology world. Somehow, it provides a natural solution for that, and such sets behave in a lot of ways like semi-algebraic geometry. But somehow now you're allowed not only look at polynomials, but also at more general. Your sets are allowed to be defined using more complicated operations, including some transcendental functions. Okay? So it's really about that. Let me also mention that, again, results are quite general, so you can allow also some differentially closed fields and things like this in order to define your groups. Okay. So what are the ingredients? How does one prove a theorem like this, and what does model theory have to do with it, right? In the statements, I don't think you saw much logic in the statements, yeah? Well, except for like propositional logic, maybe. Okay, so there are two main ingredients I mean, there's quite complicated way somehow showing that it's either one or the other, but the two main ingredients which correspond to our extremal cases are, on the one hand, improved semi-Erdös style incidence bounds. Namely, it's a more general version of asking, if I give you n points and n lines, let's say on a real plane, how many incidences can I have between them? Okay? And the same question makes sense for curves, for varieties, etc. So this is one of the ingredients which will produce us a gap in the power saving. And the other ingredient is a hierarchy generalization of the so-called group configuration theorem in model theory. And this is a general method that we have a lot of variants of this method used all the time in model theory. What they do is they somehow tell you, if I give you an operation which, for example, is associative with high probability, okay? Whatever probability means in the situation, let me not be precise for a second. But if I give you some operation which generically behaves like multiplication in a group, when does it actually come from a group? Okay? And we have various results that allow one to answer this kind of questions. So I'll give you a particular statement of this result in a second. Okay? So these are the two main ingredients. And then to connect one with the other, you have to do some model theoretic magic where you take an ultra product of finite grids and somehow you find some matroid. And either you discover that it's actually somehow a modular matroid, or in which case you can use a generalization of coordinatization of projective geometry's theorem to somehow find your group. Or if not, then you can reduce to the question when you can apply this incidence bounds. Okay? So that part is a bit technical, but I just want to highlight the two results which correspond to the extremal cases of the theorem. Okay, so the first one is recognizing groups. So I tried to extract a really, really explicit combinatorial version of the statement of this theorem. So assume I give you a group, an abelian group, okay? And consider the relation of variety R, which is just given by saying that the sum of x1 through xr is 0. Okay? Just take this relation in an arbitrary abelian group. Well, it obviously has the following two properties. So the first one, that if I fix all but one of the coordinates, then the last coordinate is also determined, right? I mean, it's clear, you can calculate it from the other ones, because the sum is 0. And the other property, again, which it is saying that if I fix any two coordinates, for example, x1, x2, and then I have two tuples which fill out the remaining coordinates, and if the sum is 0 for this one and for this one, then in fact the sum of y bar and y bar prime is going to be 0 again with any other pair of the x's. So again, obviously both these things hold, I think, yeah? Should be clear. Okay. So turns out that just from these two properties, you already can recover a group, as long as R is at least 4. Okay? So namely we have the following theorem. So suppose I fix R, and I give you a relation like this, abstract relation, no assumptions, except for these two properties, P1 and P2. Okay? Very importantly, I need to assume it for any permutation of the variables. So here I just stated it somehow with the first two variables and the rest, but I need to assume both of these properties for all possible permutations of my variables. And again, in an abelian group, it's clearly the case, right? Because you can permute. Okay. So, right. So if I give you an abstract relation satisfying these two properties, then it already has to come from the graph of addition in a group. So namely, there exists some abelian group, and we have this coordinate-wise bijections, so that R is precisely the addition in the group. Okay? In the case when all of these sets are the same, this property P1 can be viewed as equivalent to saying that the relation is a R-1 dimensional permutation of a set X1. What do I mean by this? Or equivalently, one can say a Latin R-1 hypercube. So a Latin square, for example, is just a table where you can write some numbers or some symbols vertically and horizontally. And in each column and in each row, your symbol never repeats, right? So you have, there are no repetitions. So a typical source of such Latin squares could be graph multiplication in a group, right? So what this tells you somehow is that it allows you to determine actually which of these hypercubes, Latin hypercubes, correspond to abelian groups. So this gives a complete characterization. Okay? And here I didn't talk about anything being algebraic or constructible or semi-algebraic, right? But the content of the theorem really is that if my relation itself was, for example, algebraic, then the group that I built is also going to be algebraic, and the maps between the coordinates can also be chosen algebraic. So all of this somehow can be done in the definable category in which I'm working. Algebraic, semi-algebraic, definable and non-minimal, etc. Okay? Now, to give you a very quick idea where the group comes from, it's actually not so hard to say where it comes from. For example, in the case r equals 4, note that, let's say I have a relation of variety 4, right? Because of the property P1, if I fix 2 of the coordinates, it gives me a graph of a bijection between the other 2 coordinates. So this means I have a family of functions parameterized by pairs of coordinates, for example. Okay? Now I can just fix one function like this, and I can define the sum on the functions by simply taking the composition, but in this funny order. So I have to go from x1 to x2, then I have to go back, and then I have to go back again. Okay? And with this operation, one can show, by playing with this a little bit, that the group resulting from the family of my functions under composition, excuse me, is going to be an abelian group. Okay? Now, in the general case, we are not given these real bijections. We're only given some finite to finite correspondences, which are only defined somehow generically. Let's say on generic points of some variety, or on, let's say, infinitesimal neighborhoods in some non-standard extension of my field. And then one can do something similar to what I described here, but it becomes technically more complicated. Okay? But this is roughly the idea, how one can build groups just from just given such families of relations or correspondences. Okay. And then in the general case, the group is going to live on the germs somehow, because things are only defined generically. Okay? So this is the source of groups. There are many variants of the theorem, but this is the one, I think, which is easiest to present to a non-model theorist. Okay. Now, the second ingredient. So where do we get this gap in power saving in the case when there is no group? Okay. So this comes from basically a general bound on the number of edges in the bipartite graph. Okay. So let's look at a very abstract situation. Let's say I just have a bipartite graph with parts A and B. Okay? So if I can have inside of it, I can find induced copies of complete graph with size k and k, then obviously I can have k-square edges between there, right? Okay. So now let me just rule out this worst possible scenario. Let me say that there's a bound k on the size of complete bipartite graphs, which can be embedded into my given graph. Okay? A very old theorem from '54 of Kovaryus and Turan, which is essentially application of Cauchy-Schwarz inequality, is going to tell you that we can bound it. So again, square would be the worst possible scenario. But if I forbid complete bipartite graphs sitting in there, I'm going to get a gap. Okay? I'm going to get some gap, namely 1 over k. Okay? So for example, if my graph is k2, 3, then I get the bound n to the power 3/2 from this theorem. Okay? It's actually optimal up to the constant factor. So the power itself is optimal in this theorem. Why? Well, you can entertain yourself if you've never seen this before. Just look at the bipartite relation, which is the point line incidence relation on the affine plane over Fp. Okay? And so fix P and let the prime power go to infinity. A little calculation will tell you that this is optimal already. Yeah? So of course, note that the graph is k2, 3, because if I give you 2 points, they determine a line, right? So, yeah. Okay. Somehow, unfortunately, this general thing is not enough to get any gap in the theorem that we would like to have in the power saving regime. For example, I can look at the point line incidence, but now on the real plane, okay? On the real plane, we can get a strictly better bound. So this is a semi-algebraic relation. It's k2, 3, as we just remarked, okay? And utilizing some properties of the reals, actually, which are not available in the case of, let's say, point line incidences over finite fields, we can get a strictly better bound. So namely, we can show that the number of incidences is at most n to the power 4/3. Okay? And very important mathematical fact is that 4/3 is strictly less than 3/2. Okay? And this difference between these two numbers is exactly what's going to give us the gap in the power saving when there's no group around. Okay? Well, or rather a more general version of this result. So instead of just looking at instances between points and lines, one can look at a more general situation where I have my bipartite graph, which is still k free. So for example, k22 free. But now the edge relation itself is allowed to be, for example, defined using an arbitrary algebraic or semi-algebraic condition. Or even more generally, defined in some or minimal structure. And, or even more generally, which I don't want to force too much, but we love generality in model theory. So this works equally well, for example, over the p-adics or over reals with the exponential function. So in either case, we're going to get some non-trivial gap. Again, so we get this delta, the bound of the number of instances is strictly better than what one gets just from Cauchy-Schwarz, just from combinatorics. So somehow having a little bit of geometry, well, actually not so little, but having some geometry allows you to improve this bound in a non-trivial way. And this is precisely the gap that gets created in the power saving. Now, explicit bounds on this gap are known in some special cases. They're hard to calculate in general. Well, as I already mentioned, already for some product phenomenon, we don't know the optimal bounds. But in some examples, they're known. So for example, on a plane or in a minimal structure. Okay? So in some cases, we can get this very explicit bounds. And this is where the explicit bounds in the original theorem came from that I stated earlier. OK. Now I want to tell you that not only we know how to recognize groups in model theory, but also we know how to recognize fields sometimes. Okay? So namely, let's look back for a second at this point line incidence relation. Okay? So I have my point line incidence relation over the reals. Okay? It's clearly semi-algebraic set, defined just by this formula. Not only we know the upper bound 4/3, but actually we also know a matching lower bound. So we know that the lower bound is actually 4/3 as well. So up to a constant, it does grow non-linearly. Okay? So the lower bound is 4/3 again. So it's a precise exponent. Okay? And to define this relation, we use both addition and multiplication. Okay? So we actually use the field structure, not just some group available to us. And turns out this is not a coincidence, in fact. Just the mere fact that we have some non-trivial bound at all for a relation defined using, for example, semi-algebraic conditions is going to tell us that it can only come from a field. It can only come from being able to define both an addition and multiplication just from this relation itself. Okay? So to reiterate, I give you some abstract relation, which I only tell you it's a semi-algebraic relation. And I tell you that the sizes of intersections with grids are bigger than linear, bigger than the smallest possible. Just from this, you can now define both addition and multiplication using this relation. And you can define it only using very simple operations. I'm only allowed to take Boolean combinations and projections of this relation. Okay? So this is a theorem from joint work with Abdul Basit, Sergei Starchenko, Terence Tao, and Chomin Tran. So assume I have a structure like this, or minimal. So I have my real closed field, let's say, with some additional operations on it. Okay? And assume I have a definable relation, which again does not contain arbitrary large copies of a complete hypergraph. Okay? So there's a bound on the size of those. But the size of intersecting my sets with finite grids is not as small as possible. Okay? So for example, if R is 2, this means it's not linear. It's superlinear. Then from this alone, we can actually define our field already in the structure. Somehow we can express addition multiplication. Okay? And this relies on two things. So the first thing is an improvement of the semi-Trotter bound in the case of semi-linear relations. Okay? So what this result is really saying, okay, so let's say I fix two integers, R and S, and K. Then we can find some absolute numbers, alpha and beta, just based on those. so that whenever I give you some semilinear relation, so by semilinear I mean relations which are in which I'm only allowed to use linear inequalities as opposed to arbitrary polynomial inequalities. Okay? So given a semilinear relation like this, where the complexity, so this just means the complexity of, let's say, the length of my linear inequalities, I can just count the symbols in it, let's say, and I say this is bounded. Or you can take, well, let's just say this. Yeah. Then the number of edges or hyperedges in this graph is going to be bounded by the smallest possible power, okay, so r minus 1, well, times some constant, and times some small factors, which I'm going to ignore if I only care about the power. Okay? So there are some logarithmic factors that appear. So in particular, in the case of just graphs rather than hypergraphs, what we get is that it's essentially linear. So n to the power 1 plus epsilon for an arbitrary small epsilon. Okay? So this is one possibility. Now, where do we get the field from? Well, this comes from the so-called trichotomy principle in model theory. What is it about? Well, in some sense, it's telling you that only one of three things can happen if you look at some matroid defined by algebraic closure in a no-minimal structure. What are the things that can happen? Well, it can be trivial. Where trivial, you can just think about equality in an infinite set. Okay, so, or it is modular, by which we mean that this matroid is essentially behaves like span in some vector space. Okay? Or it can be non-modular, in which a typical example would be, let's say, algebraic closure in some, let's say, over the complex numbers. Okay? So somehow these are three stereotypical cases, and this trichotomy principle in model theory tells you that in many tame situations, it's possible to show that somehow these are the only possibilities. It is not always true, but in reasonably tame situations that we understand well, one can prove that these are the only three possibilities. So in particular, if I have, if modularity fails, let's say, so I can see that my algebraic closure is not like span in a vector space in some explicit form, then we can already recover a field from it. And in this theorem, we use a particular instance due to Petersville and Starchenko, which proves this trichotomy in arbitrary minimal structures. Okay? Just to give an illustration, in a very special case, I can look at some semi-algebraic set, which is not semilinear. Then it would tell us that we can define multiplication somehow. Okay? And so combining these two facts, this essentially optimal incidence bound, and this method for finding not just groups but also fields, from model theory, we can obtain this dichotomy that I stated on the previous slide. Okay? So we can recognize groups and we can recognize fields. Okay? So somehow this trichotomy principle, which is very important for model theorists, we use it, I mean, it's used in a lot of applications. Like, for example, Hrushovski's proof of model length conjecture. Analysis of these matroids, these geometries that arise, is at the core of somehow significant model theoretic applications to other areas. And amusingly, it's completely reflected in this combinatorial behavior. So this geometry somehow can be seen just by counting points, okay, in this particular sense. Okay? So this is, I guess, the message. So thank you very much. Yeah.
Thank you very much for this very nice lecture. Are there questions or comments?
Do you know what happens if you replace, in the case of recognizing groups, definable in a minimal structure with definable in, say, an H minimal structure? So somehow, instead of the distal direction, you go in the tame topologically direction for valued fields.
Yes, thank you. Yeah, this is a very reasonable question. For H minimal specifically, I don't know, but let's say just in the spirit of earlier talk today over the p-adics. So it should definitely work over the p-adics. It's not done, but I think we know enough. We have enough geometry over the p-adics from which you should be able to recognize algebraic groups in the same way. Yeah, it's not done because there are some additional difficulties compared. I mean, we don't exactly have trichotomy theorem as given, but somehow I think it's very plausible that, let's say, for the p-adics it would work. For general H minimal, it's less clear to me, but I think it might, but yeah, I don't know.
Are there any other questions?
So actually, if you want to prove the theorem over C, you go through the reals, but do you expect better bounds when everything is algebraic instead of semi-algebraic? I mean, do you have anything that is a bit better behaved?
No, that's an amusing fact. Yeah, if you're studying these results over complex numbers, for example, somehow you do have to actually work in the reals. All the methods for proving this incidence bounds, they do rely on embedding the complex numbers into the reals and then applying this real algebraic geometry there. So it's a curious phenomenon. It's reflected by this word distal structure that I've mentioned briefly on the model theory side. I would say it's not known. I mean, sometimes it's possible to get optimal bounds through that, because somehow, once you embed complex numbers into the reals, if you count, for example, point line incidences over that, you have much more information than just abstract point curve counting. So sometimes it's possible in very ad hoc cases, but in general, it seems it's unavoidable somehow to double the bounds in that case.
More questions? No? Then thank you very much again.
Thank you.
And we have the coffee break and the